Alright, so welcome in this session, which is not that much about durability, because my talk actually is about hydration mechanism. So I am Ouzia from the EPFL in Switzerland, and in this talk, I would like to convince you of two things. So my first goal is to convince you that the textbooks are outdated about cement hydration mechanism, and my second goal is to convince you that the middle model was useful to help us understand parts of the mechanism. So in 1 hour, I believe if you just remember these two things, I'm a happy man. So first, I just want to remind you that if you want more detail, you can always come back to the keynote paper from Karen or these other papers which are published. So just as a reminder, the goal of hydration modeling research is to understand the different stages of allied hydration, which you see here. So it has been divided into 5 stages in 1968 by Kondo and Ouzia. And since then, there have been a lot of debate about what is controlling each of them. In this talk, I will just focus on first the main hydration peak, and second on the later ages period. So the first hypothesis, which is found in textbooks, is the so-called nucleation growth by impingement. And this idea is attached to the name of Avrami. So if you go back in history, if you read back the paper from the late 20s of the 20th century, Avrami was working in the field of metallurgy, and he was studying the solidification of metal. And his model was able to catch the kinetics of solidification of, let's say, for instance, here, I don't have a laser, so on the top left, you have, imagine a bath of hot copper at 1200 degrees, which is solidifying. You have a generation of nuclei which appears, and then they grow. And as they grow, they start to impinge, and then they impinge massively. And the idea behind this hypothesis was to say that as you impinge, you go from the stage 3 acceleration period to the stage 4 deceleration period. But now this is wrong for at least 2 reasons. First, so if you look at the microstructure of an allied paste after 11 days, which is way after the main hydration peak, you don't see a massive impingement of the hydrates. And a second argument, which is more, I would say, striking, was raised by Andrea Nona about 25 years ago. So he studied allied hydration at very high dilution. So at water solvent ratio 50, the grains are very far apart from each other, and therefore, clearly you don't have impingement. But still, you have a main hydration peak. So for these 2 reasons, this first hypothesis is wrong. The second hypothesis, which is also common in textbook, is the so-called diffusion barrier hypothesis. So the idea behind this hypothesis is to say that as you grow from the stage 3, you grow a layer of CSH, which at some point becomes thick enough at the peak to act as a barrier, and this is what is leading to the deceleration period. Now this is again wrong for 2 reasons. The first reason is that you don't have a uniform layer of CSH on your grain at the time of the peak. This is a picture taken by electron microscopy, and actually on the center you can still see the surface of the allied grain, which therefore is still in contact with the pore solution, so there is no isolation from the pore solution. The second argument is more technical. So if you look at an allied paste at 1 day, you have these characteristic gaps between the CSH shell and the anhydrous gap, and the anhydrous grain. And this is valid for allied, but also for PC paste. Here you have even more prominent gaps. And the idea of this second argument is the following. If you take 1 grain with a gap, the outer CSH shell around it, if it was acting as a diffusion barrier, then the concentration of species inside of the gap, so the supersaturation inside of the gap, should be higher than outside. And therefore the precipitation should rather occur inside than outside. Yet, clearly, up to the first day, you have precipitation outside, not inside. But the diffusion barrier is not only wrong for the first day, but also even after 1 month. So here you have the experiment I made in my thesis. On the left you have 20-degree experiment, on the right you have 40-degree experiment. And you have a set of curves, so roughly from the bottom to the top you have finer and finer powders. But what I want you to focus on is the difference between the dashed line and the continuous line. The continuous line are high water solvent ratio, whereas the dashed line are the low water solvent ratio. If you look at 28 days, you see that the continuous line are always higher than their corresponding dashed line. For instance, if you take the blue curve on the left, you see that the DOH is about like 70-something% for the continuous and 60-something for the dashed line. But what is important to notice is that not only the DOH is higher, but also the slope. So the rate of hydration at this time is higher at the one which has the higher DOH. And this undermines the diffusion barrier hypothesis. Indeed, if you have a higher DOH, then the layer that you have around the grain are thicker. So we would expect that you will have a lower rate, and this is not what you see here. For the same reason, dissolution cannot be limiting at this stage, because if you have a higher DOH, it means the grain can shrink more, so the surface of contact with the pore solution is lower, and again, we would expect a lower rate, but here, this is the output that we see. Right, so now I hope I have convinced you that the textbook's hypothesis, so impingement, diffusion barrier, and dissolution are not able to correctly grasp the hydration mechanism, and this is why we need more research to understand this stage. So part of the effort of my thesis was to develop such kind of model, which was helpful in some area, and this is what I will illustrate now. So this model originates in the work of Amélie Bazzoni, who was a PhD student in our team at EPFL 5 years ago, and she observed that during the acceleration period, we have nucleation and growth of needles. And these needles have characteristic growth rate, which is initially it grows fast, and then it slows down. So the question was, okay, if you combine the nucleation and growth rates you observe, can we account for the main hydration peak? Just one word on the terminology. So it's called the needle model, and I know that some people may think CSH is not needle-like, and it's a debate. But here you have a picture of a typical allied paste at 28 days. And here, in this case, you clearly have needles, because if you look like on the bottom left, you have sections of needles, so these are 1D in sections, and they belong to the grain, which is basically below the screen. Of course, in reality, there is a range of morphology, and the point is not to say you have one or the other. But the fact is, if you assume needles, you can always represent a foil as a combination of needle and not the other way around. Right, so how does the model work? So we start on the top left of the screen. You have a grain at the beginning of hydration, which is free of any kind of needle. Whenever the nucleation rate, the first plot is not 0 anymore, you have a first generation in red, which appears. And as you go to step 2, you have a second generation in blue, which appears. The first generation has grown. Step 3, you have a third generation, and the production have grown, and so on. At some points, this cylinder, these needles, are represented as filled. So it's just a representation to say that now they are growing slowly. Of course, they are always filled, but here is just to mark the difference between the fast growth regime, when they are represented hollow, to the slow growth regime, when they are represented filled. Now, if you now track the second plot, the volume of CSH, what you see is that, of course, it's always increasing, but at stage 4, you have a high increase of the volume of CSH, which is the time at which most of the surface is covered, and all the needles are still in the fast growth regime. Now, if you carry on, the first generation in red will go to the slow growth regime, and the volume of CSH will still increase, but at a slower pace. If you take the derivative of this curve, you get the third plot, which is basically the main hydration peak. And what you see is that the time of the peak is certainly not the transition from one mechanism to another one. It's just the middle of the reaction. And as a consequence, we should always consider the main hydration peak as a whole, as a single event, as Karen showed during her keynote speech. So the model works by computing the volume of CSH. So once you have to sum up all the needles over all generation and grain in the system, when you have it, you know the stoichiometric equation. You can then compute the volume of each of the other phase, so C3S, water, and CH. You know the heat of formation of each of them. You can sum up, you get the heat, you compare with the climatic curve. The input data for the model are, so of course, the size with time, the nucleation rate with time, and you also need the PSD and the specific surface. Does it work? Here is an experiment made by Bazzoni with zinc. So you have black, the curve of the halide, so on the left it's a coarse, and on the right it's a fine halide. And when you add zinc, you get the red curves. So when you put zinc into the system, you increase the height of the main hydration peak, you get a higher reactivity. But also she measured simultaneously that the needle were increasing in length, from 290 nanometer to 400 nanometer. And she raised the question, can this quantitatively account for what we see? And with the model, we could answer this question and show that it actually matched this observation quite nicely with these parameters. This was replicated by Xiaolunli, who was a postdoc in our team, and that I see there. And he basically found the same trends, and with the exact same nucleation and growth rate parameter for all of these curves, so the 4 before and these ones, we can we can grasp the experiment. Right. So the model was also helpful into understanding the impact of admixtures, which was presented 2 days ago in the keynote of Jiaping Liu, and also in the talk of Yulian, which you can see here. So this admixture basically is depressing the main hydrogen peak, which you see on the left. And as you put more and more of this admixture, you decrease it more and more. And the model will help us would guide us to spot the relevant parameter to measure, which could account for this decrease of the main hydrogen peak. So the model suggested to look at the needle length and the nucleation density. So we measured it, well, Yulian measured it, and what he found was that the needle length was the same for all curves, but the nucleation density was decreasing when you put more of these admixtures. We put them as parameter into the model, and we could grasp the trends of the admixture on hydration. Right, now I'm going to the later ages part, so how it was useful to understand the later ages mechanism. So one thing which is important to do in the later ages is to distinguish between what I call the external and the internal space. So on the left you have a PC at 1 day, and whatever is in the gap I call the internal space, whatever is out of the shell I call the external space. So you have in black on the right the internal and in red the external space. Now, here is the $1 million question. Actually, it is one Prosecco question, so if you answer right, you will get it. And Karen, you don't answer the question, please. So imagine you have a 10 micron grain at water solvent ratio 0.32, which is to the scale on this image. You open a 1 micron grain. My question is, what is the volume fraction of the 8 micron grain divided by the volume of the 10 micron grain? You have to raise your hand. 0.5. Okay, right, that's correct. It's 50%. So you will get the bottle. Did you read the paper? Or? So yeah, indeed, and maybe it's not as obvious as it sounds. The first time I just made the comparison, and then I back-checked and I checked again, and yes, when you open the 1 micron gap, you do have 50% of hydration. So when you look basically at the image like this, you may not realize that these gaps have an importance, but they do have, so you need to consider it. Right. So now, if you make the computation, so you open a gap, then the water will get in, and then you have to subtract further the water which was consumed for, to produce the hydrates. So when you do the math, you get this formula, DOH equal 1.6 times the water to solvent ratio. So this means that whenever you reach this threshold, the external space is completely filled. So you cannot have more hydrates in the external region. You can densify them if you want, but you cannot produce more. Does this rule of thumb work? If we come back to the experiment, so this rule of thumb applied to 0.32 water solvent ratio gets you these black lines there. And as you can see, the dashed line and the continuous line split at this, yeah, I'm finishing. Yeah, the last, format the last slide. So, the black line are the, this rule of thumb, and the dashed and continuous line split exactly, I mean, not exactly, but close to this line. As you can see, both at 20 degrees and 40 degrees for 16 curves. So it's quite convincing. All right, so with this, I hope I have convinced you, first, that textbooks are outdated. Neither impingement nor diffusion barrier nor dissolution are the leading mechanism, and that the middle model was helpful to understand parts of the mechanism, even if, of course, there is much more to be done. If you have more information, please, you can refer to this keynote paper or our paper with Karen earlier this year, or if you want my own thesis with all the details, just send me a mail and I will be happy to answer you, or you can ask me a question, of course, just right now. Before I finish, I just want to acknowledge my whole team, Professor Karen Scrivener for the opportunity of having been at the lab for the past 4 years and a half, my office mate Julia Stone, with whom I talked a lot, and also Elise Berodier and Aaron Muller for their help. Thank you for your attention.